This is the topic Modern Physics and the section called Particle, AntiParticle, Annihilation. Now, what will be happening here, I'll be talking about how the mass of a particle and the mass of an antiparticle can be converted directly to energy. When the particle and the antiparticle meet, they annihilate each other and become energy. They are converted to energy. So again, if their mass is converted to energy, what equation do you think we're going to be using? That's right. We'll be using our old friend E equals mc squared. So, let's see how this works. Now, first of all, it's very important that you know that every particle has a corresponding antiparticle. Every particle has a corresponding antiparticle. That antiparticle has a charge of the same magnitude. The charge is the same magnitude, but opposite sign, and the masses are the same. All right, so what do we got here? We've got a particle and the antiparticle. The antiparticle's charge is the same number, but opposite sign. So if the particle is +1, then the antiparticle is -1. The masses of the particle and its antiparticle are the same. So the charge, same number, opposite sign. The masses are exactly the same. There's no such thing as negative mass. Okay? So here we go. Let's look at some examples. Let's look first at the proton and the antiproton. All right, so the proton. We can look up his mass on the front of the reference tables. Top box, down near the bottom, rest mass of the proton, 1.67 times 10 to the negative 27 kilograms. So the mass of a proton, 1.67 times 10 to the negative 27 kilograms. Now, what about an antiproton? He's going to have the same mass. His mass is going to also be 1.67 times 10 to the negative 27 kilograms. Now, the charge of a proton, Q, for the proton, we could write it +1e or +1.6 times 10 to the negative 19 coulombs. If they ask for it in coulombs, make sure you put Q in coulombs. Now, what would the charge of the antiproton be? Same magnitude, 1, opposite sign, negative. So, the charge of an antiproton would be -1e, or -1.6 times 10 to the negative 19 coulombs. The proton and the antiproton. Now, I'd also like to draw a diagram. Oh boy. of a proton and an antiproton. Here's the proton, a big heavy particle, and here's the antiproton, also a big heavy particle. They are, after all, the same mass. Picture of a proton, picture of an antiproton. All right? Now let's look at an electron and an anti-electron. Now remember, if the proton and the antiproton come together, they're going to annihilate each other. But we'll do that later. It's a little dangerous. I want to be careful. All right, the proton and the antiproton. Now let's look at the electron and the anti-electron. Okay, the electron has a mass of 9.11 times 10 to the negative 31 kilograms. That's his mass. He's much lighter than the proton. Now the anti-electron has the same mass. The anti-electron also has a special name. The anti-electron is called a positron, and his mass is the same as the electron. That's the mass. Now what about the charge? We know that the charge of an electron is negative 1e. That means that the charge of an anti-electron must be positive 1e. The charge here, negative 1.6 times 10 to the negative 19 coulombs. The charge of this guy, positive, right? Positive, same magnitude. Students, remember that magnitude just means number. Magnitude means number. 1.6 is the magnitude, 1.6 is the magnitude. The negative is the sign, the positive is the sign. 1.6 times 10 to the negative 19 coulombs. I'm sorry, the number, it would include the exponent. 1.6 times 10 to the negative 19 is the magnitude. 1.6 times 10 to the negative 19 is the magnitude. Now, let's draw a picture of an electron. He's a tiny little negative guy. And a picture of a positron, a tiny little positive guy. Now remember, we drew the proton as a big positive guy, and the antiproton as a big negative guy. The electron and the anti-electron are little guys. Okay? So an anti-electron is not, I don't even want to say it, I don't want to confuse you. All right, an anti-electron is also called a positron. He's called an anti-electron because he's little, has a small mass just like the electron. We call him a positron because he is positively charged. All right? If I may, hopefully without confusing you, all right, this is a proton, this is a positron. The proton's mass, 1.67 times 10 to the negative 27 kilograms. The positron's mass, 9.11 times 10 to the negative 31 kilograms. Their charges are the same. Their charges are the same. That's a proton. That's a positron. Okay? All right. Let's talk about what happens when a particle comes into contact with its own antiparticle. Oh, I'm sorry. One other little thing I should mention is that the charge of an anti-neutron would be 0, just like a neutron. The opposite of 0 would have to be 0. So an anti-neutron would have the same mass and actually the same charge, because the opposite of 0 is 0. So, enough said about antineutrons. All right, now, what would a proton and an antiproton be composed of in terms of their quarks, their constituent particles? Right? A proton would be U, U, D, while an antiproton would be anti-U, anti-U, anti-D. Now let's add those up. This would be positive 2/3, positive 2/3, negative 1/3. Remember, we're looking all of this up. We've memorized the proton. I'm teaching you the antiproton now. And these charges we've looked up on the reference tables, the charges of the quarks on this reference table, particles of the Standard Model. All right, we add all this up, the charge of a proton, positive 1e. Since e is 1.6 times 10 to the negative 19, 1 times that is positive 1.6 times 10 to the negative 19. Now, an antiproton. Up antiquark, negative 2/3. Up antiquark, negative 2/3. A down antiquark, the opposite of that, positive 1/3. Add all this up. The charge of an antiproton is negative 1e, which is negative 1.6 times 10 to the negative 19 coulombs. Okay? All right, now, let's see what happens when the proton and the antiproton come together. No, I said that earlier. I wanted to do this in the meantime. All right. Now, we know that when matter and antimatter meet, they are converted to energy. And the equation that tells us how much energy is E equals mc squared. Now, what would the mass be of a proton and an antiproton? Well, they both have the same mass. So you could either say, all right, 1.67 times 10 to the negative 27 plus 1.67 times 10 to the negative 27. That's the proton, that's the antiproton. This is the mass. The mass, not the charge. The charge would cancel. The mass of the two of these would total, all right, let's add it together. All right, 1.67 second E negative 27 plus 1.67 second E negative 27, and we get 3.34 times 10 to the negative 27. This is the total mass that will be converted to energy when the proton and the antiproton come together. The other thing you could do is say 2 times 1.67 times 10 to the negative 27. If you do that, you will get the same 3.34 times 10 to the negative 27. Do not square this. It would be a mistake. It will come out wrong. There's 2 of them. Either add the 2 together or multiply the mass of 1 times 2. You get this answer, the right answer. So, this is the mass that we're going to be putting in here to convert to energy. All right, so let me get rid of this so we have a little more room. All right, 3.34 times 10 to the negative 27 kilograms. C, the speed of light, is listed on the front of your reference tables. Go look it up. All right, 3 times 10 to the 8th meters per second squared. The most common mistake, you're going to forget to square. Don't forget to square. Okay? Another common mistake here would be to put in the mass of the proton and forget to double it, because you've got a proton and an antiproton. A lot of students put in the mass of the one proton here, and of course that comes out wrong also. So let's do this and square it, then multiply by this. All right, 3 second E8, square that, equals, all right, times this, 3.34, second E negative 27 equals. All right, 3.006 times 10 to the negative 10 joules. All right, that's how much energy we get when the proton and the antiproton annihilate each other. They come together and their mass is converted to energy. So now they weigh nothing and it's all energy. All right, now, you could also do this with an electron and an anti-electron, otherwise known as a positron. You would take the mass of an electron, double it, put it in here, and find out how much energy you get in joules. You can also do it with a neutron and an anti-neutron. Double the mass of the neutron, put it in here, and you'll figure out how much energy. It'll come out pretty much the same as a proton and an antiproton because they do have about the same mass. The neutron is slightly heavier. So depending on how many significant figures you're using, you're going to get the same answer when you do the neutron. Maybe just a little bit more energy. Now, very, very important to this discussion of particle, antiparticle annihilation is how come two protons can't annihilate each other? Well, let's first prove why it's okay for a proton and an antiproton to annihilate each other. Let's bring up something called the law of conservation of charge. And like any other conservation law, the law of conservation of charge basically says in third grade, charge cannot be created nor destroyed. But we're not going to write that on the Regents exam because that's a third grade statement. On the Regents exam, you might write something like this. The total charge at the beginning of a process equals the total charge at the end. So, when we say in third grade that energy cannot be created or destroyed, or charge cannot be created or destroyed, what we mean in a more sophisticated way is that you don't create any charge, so you don't get any more, and you don't destroy any charge, so none of it goes away. So, since you don't get any more, you don't destroy any, the total charge at the beginning equals the total charge at the end. All right. Now, let's see how this is fine for a proton and an antiproton. How is the law of conservation of charge upheld? The word upheld means that the law of conservation of charge is proved to be correct. And it has to be because it's a universal law that does not get violated. All right? It's something that happens in nature all the time. So, if in the beginning you have a proton and an antiproton, the total charge at the beginning is 0. At the end, you have energy. Well, energy has no charge, so the total charge at the end is still 0. The law of conservation of charge was upheld when the proton and the antiproton annihilated each other because the total charge at the beginning was 0 and the total charge at the end is still 0. Now, what would be the problem if you tried to get two protons to annihilate each other? What would be the problem? What would be the problem if you tried to get two protons to annihilate each other? Well, the charge at the beginning would be +2. The charge at the end would be, well, energy has no charge. Oops. This would violate the law of conservation of charge. So this does not happen. All right? So, what did we talk about in this section? We talked about how matter and antimatter annihilate each other when they come together. What we mean by annihilate is that the matter is converted to energy. I don't want to use the word disappears. It doesn't disappear. The matter is converted. Use the word converted to energy when you write about this process. We talked about how a proton has the same, let me back up a minute. We talked about how every particle in the universe has a corresponding antiparticle. That antiparticle has the same magnitude of charge but opposite sign. So if the proton is +1, then the antiproton is -1. Same magnitude 1, different sign, positive, negative. The masses of the two particles, the proton and the antiproton, are the same. Right, so again, for particle and antiparticle, the charge has the same magnitude but opposite sign. The masses are the same. This would be for a proton and an antiproton, an up quark and an up antiquark, an electron and an anti-electron, his buddy the positron. And when the two come together, they annihilate each other. You take their total mass, which usually means just doubling the mass of one of them, take that total mass and convert it to energy. Make sure when you plug into E = mc² that your mass is in kilograms. Your energy will come out in joules. If you put in energy, you're going to get out mass. Make sure you put joules in. You'll get kilograms out. Now, be careful, because the amounts of energy that you're creating here are very, very dangerous. I will see you in the next section.